Hey guys, so in this lesson, we're going to be looking at the fetch, decode, execute cycle, which is a cycle we've obviously learned about before, but we're going to go to a further detail to see how it actually is going to work. So we've got the straightforward cycle where we have something fetched, decoded, and executed. What are we fetching? We're fetching, in terms of what we learned at GCSE, either data or instructions. Data to act upon, instructions to commit some kind of action. And then we decode, we figure out what we're supposed to be doing with it. So what those zeros and ones are going to be, and then finally execute. And this is what repeats over and over again. From our perspective now, we are going to a deeper level, and when we're looking about how this actually happens and what the specific registers are that are going to do it. Now, if we're thinking about fetching, where's it going to fetch from? So we've got memory. Now this memory, maybe it's RAM, maybe it's cache, but it's something where the CPU can directly fetch from, and I'm going to represent it by just drawing a little grid to represent this memory. Sometimes this is referred to as the sometimes it's referred to as the IAS. That's short for immediate access store. Sometimes it's just referred to as memory, okay? Here, this is a representation of memory. And inside of here is an address, a physical address in memory that will contain our ones and zeros. Now, because it's using von Neumann architecture, one of the big implications about von Neumann architecture is that memory contains both data and instructions in the same place. So this could be holding an instruction, or it could be holding data in this location. And what we're going to do is with this data needs to be fetched, then decoded, finally executed. And now we're going to have a look at the registers to allow us to achieve that. In my computer model, my registers work under a 6-bit bus, i.e. I only have, it's sometimes called word length of 6 bits, i.e. I only have, an instruction can only be 6 bits in length, a bit of data can be 6 bits of length. Truly, this would be a terrible computer, but it helps us, it'll be a simplified version. And so what's going to happen is we're going to have something where these registers here, which I'll go into detail in a moment, will be fetched. If data is going to be moved around a computer, how is it going to be moved around? So we're going to use buses to move data around. And at GCSE, you just learn that you use a bus. At A level, you have to learn about 3 specific buses. So we have 3 separate buses. We have the data bus, the address bus, and the control bus. And they all do slightly different functions. The control sends out impulses from the control unit to help synchronize the movement of data along. Now, you can imagine we're moving data from one register to another. We all need these things to happen exactly at the same point on a clock cycle. If this moves too early, so this hasn't quite moved yet, and it gets updated from one here, then you'll lose that data. So when this register passes its data to this one, it needs to happen at the same time as this one is passing down to this one. The control bus sends control signals to synchronize that movement of data. Now let's have a look at our individual registers. The first register, confusingly called, is the PC, and that stands for, it does stand for personal computer, but in this context it stands for program counter. Now the program counter, it doesn't hold an instruction. It holds the address of the next instruction you want to use. So it's not the instruction itself, it's the address of where you're going to find it. A bit like that song, this is not the greatest song in the world. This is a tribute to the greatest song in the world. It's a reference you might get if you're 10 years older, but you're not. The program counter is going to hold an address. So in this context, let's give it a... So this here is the program counter, and it's pointing to position 1. Now let's look in our memory here. Let's say that position 1 is here. This was position 0, position 1, 2, 3, 4, 5, 6, 7. So there's a byte on every row here. So that's position 0. So what has to happen is that it's referencing this position. Now, the next thing that happens is that this value here needs to be copied into the register below. Now, what was the next register? So the acronym was MAR, memory address register. Okay, the first thing's got to happen is that the contents of this register are copied into the MAR. Which bus do you reckon is going to use to do that? The data bus moves it from one to another. So down here it goes, and so this is the first thing that happens is that data is copied from here into here. So the contents are now in the memory address register. The deal with the program counter is this, is at the end of the processor cycle, it has to increment. By that, it just means it moves up by 1. So we'll remember to come back to this, because the program counter only does two things, holds the address of the next instruction to be fetched, and increments. But it's supposed to happen at the end of the processor cycle, so we'll come back to that. Now this, the MAR, this is holding the address, but what we need to do is then fetch that address. So where is this? It's pointing to position 1, which was here in memory. So what bus do you think we're going to use to go get that stuff? Address bus. So we're going to use the address bus. So the address bus is used to fetch what is contained inside that address. The stuff inside that address is then going to be put into this next register. Anybody know what the name of the next register is? MDR. So the contents from here are copied into the memory data register. Which bus do you suppose is going to be used? Data is going to help copy it back in here. So here we go. Data is going to copy in. So contents are then put back into the memory data register. Now the control bus, when have I shown it being used? Now the contents of what was ever in that box was put into here. Now, could it be an instruction or could it be data? Because it's von Neumann architecture, it could be either. In this situation, I'm going to say it is an instruction. So it's going to be 0, 0, 1, 0, 1, 0. And we have to take a moment to think what an instruction, we need to take a moment to think about how instruction is formulated. Okay, so over here, we now have our instruction. In fact, why don't I just duplicate the one we just had? So it's 0, 0, 1, 0, 1, 0. There are two sections to an instruction I was just described. We have the operand and the opcode. So I'm going to say this bit in red here, that is the opcode. Now the opcode is the bit that tells it what to do. It could be to add, to sub, to output, to input, to store, etc. On the other side, I'll shade it in blue. This bit is the operand. The operand is the value it's applied to. So if it could be to add, it could be add to that value. It could be adding it to a particular memory, a bit of a section of memory to find the address. It could go either way. Let's take a moment to think about this. If I ask any of you to 001, you go, what? And if we come back to our cycle started with fetch, but then it went to decode. And so this is what we're talking about. We're trying to what does that 001 actually mean to do? What does the 010 mean to do? So this is the decode element. And let's take a moment. I'm going to create my own little instruction set. Now, an instruction set is different for different processors. There are some agreed sets, like the ARM v7 set, which is all ARM processors, whether it's inside a Apple device, mobile device, or an Android mobile device, they typically all use the same one, which is when, let's say you go for a more advanced processor, it does things faster, but it still uses the same instruction set. Same with x64, x86 type processors. So let's do this. So we've got, I've got what the opcode is and the mnemonic. If you remember, a mnemonic was a shortened way of describing a function, like to add, to subtract, etc. Comes into things like assembly language. That's where mnemonic comes in. Silent M, Y, I don't know. Just the way it is. Just accept it. So I've got a 3-bit opcode, so therefore I can have 000, 001, 010, 011, and I could go for another 4. But let's just stay here. And I'm going to invent I'm going to describe what my instruction set does. 000, that's to input. 001 is to add. 010 is to store. 011 is to sub. Yeah, it's meant to be sub. There we go. And there'll be some other instructions, but those are the ones it can do right now. Those are the opcodes. Equipped with this new knowledge, we can now figure out what it is that we're supposed to be doing with this instruction. So this opcode says to 001, So we can go to our instruction set, and we can say 001, it means that it's asking us to add. Okay? A little bit of planting ideas for the future. There's two types of families of processors. There's something called RISC processors, that R-I-S-C, and there's something called CISC processors, that's C-I-S-C. We'll come back to it later. With RISC, it says you've got a reduced instruction set, i.e. you haven't got many instructions. Would you say that's not very many? So this is actually a what type of processor? A RISC processor. CISC processor stands for complex instruction set computing, and you'd have a lot more instructions. There's other things, but that's just for the future. Okay, so we know that we want to opcode, but we also got to sort out this operand bit. But let's go back to our journey through the different registers. So last place we were at this memory data register. We need to then pass the contents of the memory data register down to the next register. Does anybody know what the next register is called? Thank you, Karis. Spot on. Question, people. The contents of the MDR got put into CIR. How did that happen? Not by teleportations. Things are bussed around. There are three buses, the data bus, the control bus, and the address bus. Data. So data buses, because data buses is what moves data around from register to register, a data bus is used. And data buses move it around here. And we talked about address bus over here to locate this part in memory, the address of it. Control bus, again, I've not mentioned, but control bus is essentially sending a signal every time this happens to, the word is synchronize the movement of data. And I said right at the beginning, for instance, let's say, now we've got a bit more flesh on the bone, if we said the memory data address register is going to copy into the memory data register, yes? It's going to find it and do it. Well, what happens if the program counter hadn't updated this yet? We'd find the previous one again. And then that will go in here, and you can see how that's going to cause a massive issue. You know blue screens of death, when the computer just completely fails? These often happens when you get the clock speed faster than its parameters and you've overclocked too far. Causes blue screens of death because the cycle's happening quicker. Because what's happening is that this loses synchronicity, i.e. you get something where it pushes over. When you think about it, it's happening 4 billion times a second. It's only going to happen once, and then it will crash on you. Anyway, but so the control bus is constantly sending signals at every stage to synchronize it, okay? Because the control bus, where do you think it's coming from? What bits of the compute? What about other bits of the CPU have we not discussed? Control unit and the ALU are the two bits, aren't they? So we've got control unit. Control unit is serving two purposes here. Purpose number one of the control unit is that it sends control bus over the control bus sends synchronizing signals. And the other thing it does is it lets us decode the instruction. So when this data, this opcode element, can be sent to control unit to figure out what to do about it. Okay, so that helps us decode. I'm actually at the end of the fetch cycle right now, so before I forget, what other thing did we say was going to happen with the program counter? We said that, there you go, so it increments. So this program counter here does two purposes. Purpose number one, passes the data down. Purpose number two, increments. And so let's just do that really quickly. It increments, which means literally it goes up by one. And so the next place in our address where it's going to come to, so the next bit in memory it will reach is here. Now I want you to appreciate something for a second. When the program counter is working, it's going to go here, then here, next instruction here, next instruction here. See, they're stacked up one after each other. Now think about for a second. That will work for one process that you're trying to do, whatever it happens. I don't know, I'm opening Chrome and it's loading up all the different elements to load Chrome up. But then if I move my mouse, is that the same thing? That's a different set of instructions. So actually, all the ones for Chrome are getting stacked up here, but maybe my mouse movement, for instance, is down here. You'll need to have something called an interrupt or jump instruction to make it jump from here down to here. If you don't have that jump instruction, what's going to happen is it will have to do all the things of loading Chrome, and then your mouse will start going all over the place, right? So just an implication of the program counter, because all it can do is increment, sometimes it can receive inwardly a jump instruction. That might be because you're multitasking. Might be because you're doing something that's more essential. So you have interrupts. So you've got something like, I don't know, maybe you're or actually using a mouse as an example for that. It's an input-output instruction. Have you ever noticed that your system could be crashing, but you can still move your mouse pointer around? That's because your mouse pointer is a higher priority interrupt, and therefore it will jump and do those things, while in the background it's still stuck doing whatever the thing is. All right, let's... We were down here with the current instruction register. This bit over here, this control unit part, that's going to come down here to be decoded. It'll still be a data bus element because it's still moving data inside the CPU. But we have moved from one cycle to another. What part of the cycle are we on now? We're on decode. We're figuring out what to do with it. So what's going on here is actually decoding. Well, the CIR is where the decoding starts happening, for sure. So this bit, the opcode, goes to the control unit to figure out what it is that we're trying to do. Maybe it's to add, to sub. What were the other two? Add, sub, store, and input, or something. One of those four. What about this bit on the right? So this... What is this bit on the right? It's the operand. Now, we got a bit of a conundrum here, okay? The operand depends on what kind of addressing mode. So I'll go into it now, because you might not get it straight away, but that's fine, because now you've got me recorded and you come back to it. It depends what kind of addressing it's got. Now, there are three addressing modes we care about right now. In fact, let's zoom in here. There are three types of addressing mode. So there are three types of addressing modes: immediate addressing, direct addressing, and indirect addressing. And that says, what are we going to do with these values here? If it's immediate addressing, then it takes that value and it literally is the value. So that, in this case, would be the value 2. So if it was immediate addressing, we'd say we want to 001, we want to add, so add 2. So we'd have to take something from the accumulator, so from the AC. We take the value from the AC, we take this value 2, we take them to the, what's this down here? ALU, thank you. We take it down to the ALU. We take the value from the AC, let's give it a value. It's got 1, 1, as in not 11, as in 2, as in 3. That 0, 0, 1, 0 goes in here, the 1, 1 goes in here, the value goes in, updates the accumulator, and that's how that instruction happens. But if it's direct means something different. In direct, it says 2 refers to where we're going to store the value. Now, the program counter went up to 2, so you're thinking you're going to fetch an instruction, but actually, 2 in this case is where the actual data is stored. So this would be a stupid idea, that you're actually saying that the program counter is pointing to the next instruction to be fetched, the address of the next instruction to be fetched, but it's also saying that's where the data is going to be stored. Do you think that's going to cause a problem? This is one of the big issues with von Neumann architecture. Because data and instructions are kept in the same place, this is really silly. And when we do little man computing, which is simulating von Neumann architecture, you can totally do that, and it will totally break it. So actually, that's the problem. In this context, yeah, it will break it, because it will override the instruction. So then you try and fetching it, but it's not instruction, it's data. In this context, though, we're saying we are fetching it. Here's what happens. If it's direct, we need to fetch it, don't we? Voice broke. We need to fetch it. So actually now we need to almost do a cycle within a cycle. Which register do you think we're going to put it in to let it fetch? Memory address register. So now, because if it's direct addressing, we need to then take this and copy it into here. So this is going to copy it into here. And now the contents of the memory address register is going to be, oops, that's a bit, I brutalized it. It's going to be 1, 0. Okay? And then what bus are we going to use to retract the information? So we need to go into the memory. So what address bus? So this address bus will then go over here, find the contents, what's inside that box. The contents of it there, which is no longer instruction, what are we fetching? We're fetching data now. That data is going to be copied from here and then put into the MDR. Something I want you to notice, with immediate addressing, what was the largest value I could make? 7. Because I've only got 3 bits. Now that I've fetched the instruction, I can actually use all 6 bits. So I could have a 60, up to 63, yeah? 0 to 60, 64 different values. Okay, so that's an advantage. Here's something else. Now I can update and change what's in that box, replicating the functionality of a variable, because now I can update what's inside that box. Here, could I update that value? Not really. With immediate addressing, it's more like a constant. But the advantage is, what is the one advantage you think of immediate addressing? It is faster, it's immediate. This way, I'm having to do another cycle within a cycle, aren't I, to actually fetch the instructions. But now we're at the point to be able to do it if it was direct addressing. We know we want to add. We know we want to add what's in the accumulator to what's in the memory data register. Those are 2 sent to the ALU and sent back again. Since we're here, let's talk about what would be different if it was using indirect addressing. I want you to notice something. How many different addresses can I actually access by using direct addressing? I can use these 3 bits. So from 000 to 111. I can only access this bit here. So I can only access, if I shade it in, I can only, no, that's not shading. If I can shade it in, I can only access those. Yeah? Well, what happens if I want to access this data here? Do you see the issue? Can't do it. But if I take the contents of what's inside that box and copy it here, how many different places can I access now? 64. That's what indirect addressing is. You fetch the contents of what's inside an address in memory, but you're not extracting data, you're extracting another address. So in this case, what is this going to be? 3, 8, no, that's an 8. Yeah, 8, 16, 24, 27. Yes? And then that is where you'll find your bit of data. So, I don't know, that's 8, that's 0, 7, I don't know, down here somewhere. Let's say this is the content. It's this box here. That's what indirect addressing is. But, okay, what's going to be faster, direct or indirect addressing? Direct. So immediate's going to be the fastest because you've immediately got it to use. Direct's going to be the next fastest because it's just got to do one cycle. Indirect addressing is even more of a pain because you've got to get this bit here, which will find another address in memory, which then you have to find another we have to then go into to get the data from. But it is long, but with indirect addressing, what's the one big advantage? You can actually access all your memory here. Okay? While with direct addressing, you're limited with a number of places. What's going to happen, though, is you can still only access 7 different places, but of course then they can point, basically what's happening is then they point to different locations. That one can be pointing to this one, that can be pointing to this one. At any one time, there are only 8, but then of course you can change what's inside the box.